Okay, our next and the last talk for today will be given by Raul Quiroga Barranca from CIMAT, Mexico, titled Bergman Spaces, Toeplitz Operator, and Differential Geometry. Please, Raul.
Yes. Thank you, and for organizing this mini conference. I'm sure it's going to be very, very nice. Many ideas are coming up. So I'm going to talk about Bergman spaces, Toeplitz operators, and most importantly, its relationship with differential geometry, Lie theory. It's not just that it appears, but you can actually use differential geometry, Lie theory, representation theory to solve some interesting problems. So that's the table of contents for my talk. First, some definitions, very basic, really. Some of these have been mentioned by Nikolai already, but I can point out some interesting features. So in the rest of the talk, D is going to denote some bounded domain. At some point, I'm going to assume some extra conditions on this bounded domain. This gives you in analysis. You have the L2 space with a normalized Lebesgue measure and the space of holomorphic functions. The intersection gives you the Bergman space, L2 and holomorphic. Now there are some interesting points to make here, very elementary, but important still. On one hand, you have a Hilbert space for L2. Point evaluation does not make sense because you only have classes of measurable functions, and holomorphic functions is a Frechet space for the topology of uniform convergence on compact subsets. So evaluation is everything. Somehow these together work very fine in the Bergman space because of this result. The point evaluation on the Bergman space is not only possible, but it's a continuous functional with respect to the L2 norm. Further, any compact subset, there is some constant so that the uniform norm of the elements on the compact set, the elements on the Bergman space, this norm is bounded by the L2 norm with this constant. That's the reason to have the following consequence. This space, the Bergman space, is closed in the L2 norm. It's a Hilbert space. This was already mentioned by Nikolai, also mentioned by him. Because of this situation, evaluation at a point can be given by inner product with respect to some function in the same Bergman space. This function depends, of course, on Z, this case Z. And out of that, you get your Bergman kernel, which is a function on D times D given by this expression. It is holomorphic on this variable because of the choice of this function. And there is some Hermitian symmetry satisfied by this Bergman kernel. If you interchange the two arguments, then you get a conjugation. So this Bergman kernel is anti-holomorphic on the other entry. Because of this symmetry, the orthogonal projection from L2 into the Bergman space is given by this expression. Here is hidden the inner product with respect to this lowercase k. The so-called Bergman projection. In particular, we have a reproducing kernel formula. Every function on the Bergman space can be somehow written in terms of itself using this Bergman kernel function. Because of that, Nikolai also mentioned this, the Bergman spaces of this form for bounded domains are what is called a reproducing kernel Hilbert space. And this BD is the corresponding Bergman projection. So this, of course, lies very nicely in the setup that Nikolai mentioned. You have a large Hilbert space, a subspace, which is actually nicer because of this property, and you can project some operators acting on L2 of D. That's how you get Toeplitz operators for essentially bounded symbol A. This is the definition of the Toeplitz operator. First multiply by the symbol and then project back to your Bergman space. So this is just the very basics of this theory. Now, the thing is that you can consider families of Toeplitz operators and the C-star algebras that they generate, and this turned out to have very interesting features, very remarkable features. Of course, Nikolai already mentioned some of this, and let me mention a couple more of this. So here I have a bounded domain, the space of essentially bounded symbols, and this T is just the space of Toeplitz operators, not the C-star algebra, just the Toeplitz operators. Then there are many, many results that you can say about this and the algebra that it generates, but I'm going to mention some results that I found very interesting due to Miroslav English with this generality. First of all, a strong operator topology, the closure of the space of Toeplitz operators is all of the bounded operators. So even though you have a very special way to define these operators, you have some density, at least in the strong operator topology. The norm closure, that's stronger, of course, of the space of all Toeplitz operators contains all compact operators on this Hilbert space. And on the other direction, not so big, the C-star algebra generated by this is not all bounded operators. It's a proper space in all the bounded operators. So even though the Toeplitz operators are kind of, might seem to be restrictive, they are very general. They give you a nice large family of operators to study. Because of these results, you have somehow a concrete family of Toeplitz operators on Hilbert space that are worth studying. So that's a reason to consider, these are some of the reasons to consider Toeplitz operators. Of course, there are many other reasons. Somehow, this mini conference is going to be a whole explanation of why Toeplitz operators and their derivatives are interesting. But now, let's get into the geometry. The geometry comes from the geometry of bounded domains. So I'm going to explain the Bergman metric, the Carton metric associated to this, and this special type of domains, the bounded symmetric domains. So we start with this notation, the group of biholomorphisms like this, the automorphisms of the bounded domain. Bergman kernel satisfies this symmetry with respect to the automorphisms. Is not precisely invariant, but it satisfies this expression with the complex Jacobian, the determinant of the complex differential. This is a notation I'm going to use several times. This is just really using change of variable in the integral expression for the Bergman projection. It's a very natural geometric structure on the domain. How is that? You can consider a Hermitian matrix by taking the logarithm of KCC. This is a positive function, always. That can be proved. Compute the complex Hessian of that. It turns out to be a positive definite matrix for every C in D. So this positive definite Hermitian matrix gives you at every point a Hermitian inner product. And that's how you get what is called a smooth Hermitian metric. This is the definition once you have these positive definite matrices. It's changing with the point, but it varies smoothly because of this expression. This is called the Bergman metric of the domain. So kind of just for free from the reproducing kernel property of the bounded symmetric domain, the Bergman space on the bounded domain, you get this Bergman metric, some geometry. Geometry is very nicely related to the holomorphic properties of D because of this property. The automorphisms preserve this Hermitian metric in this sense. You take the differential, move around the tangent vectors, you preserve the inner product. In symbols, this can be written like this. The automorphism group, just the biholomorphisms, is contained in the isometry group of this Hermitian manifold. So right away, you get some geometry from the different spaces. You can get even more. So here I'm kind of using a more general setup. Consider some complex manifold. So just holomorphic changes of variables with a Hermitian metric. You can associate to this Hermitian metric two real value tensors. Just take the real and imaginary part. I usually consider this kind of normalizations to simplify some computations. Real part is going to be a Riemannian metric. On the other hand, the imaginary part, because of the Hermitian properties of H, is going to be a two-form. This is symmetric G, this is anti-symmetric. The tensor G is always positive definite, so you get a Riemannian manifold. You can talk about geodesics, curvature, isometries, things like that. And on the other hand, this two-form, because it comes from H, which is non-degenerate, is always non-degenerate. If furthermore it is closed, then you say that your manifold is a Kähler manifold. So a complex manifold with a Hermitian metric, you compute the associated two-form. If it is closed, you get a Kähler manifold. That's some general definitions. And that provides you with an example of what is called a symplectic manifold. A symplectic manifold is an even dimensional real manifold with a two-form which is non-degenerate and closed, which is the case in this situation, of course, when you have closeness of this two-form. Now, this is a fundamental fact. A bounded complex domain with its Bergman metric is scalar. It is the closed two-form that we obtain like from the Bergman kernel is always closed. So back to this expression over here, somehow that comes from the fact that the metric is defined in terms of a Hessian. Because of that, the corresponding two-form that is obtained by taking the imaginary part of this is closed. And you get, for bounded domains, you get symplectic geometry, not just Riemannian geometry. Preserve the Hermitian metric, and so they preserve the real and the imaginary part. They preserve the Riemannian and the symplectic structures. Now, I want to consider these other domains, the bounded symmetric domains. A domain D in Cn is called a bounded symmetric domain, BSD, if it is bounded, and the following condition is satisfied. Somehow this condition is saying that there are lots of symmetries for your domain. The easiest way to do this would be to consider bounded homogeneous domains, but somehow that's not enough to get a good collection of bounded domains. We consider this other condition symmetric, which means following: you take a point, then there is a biholomorphism of the domain, which is involutive, its square is the identity, fixes the point, fixes no other point. So for every point, there is some kind of biholomorphic reflection around the point. That's the idea. And you can take 2 points, consider kind of the middle point, for example, using geodesics, and reflect in that point, then you interchange the two extreme points. Because of that, bounded symmetric domains turn out to be homogeneous. These are very, very nice domains. You have a large enough class of domains, but not so large that you cannot classify or get a hold on the domains. Examples, that's very important. The unit disk that somehow Nikolai considered before. The unit ball, of course, he also considered that. The unit ball and Cn. There are many other bounded symmetric domains, but let me mention this just to have some more abstract example in mind. This Carton matrix domain. So you consider matrices of size m times n and impose this condition. Z times C conjugate transpose is less than Im, which means that the difference is positive definite. The difference is clearly Hermitian. You require it to be positive definite. Of course, this restricts for the correct values of m and n to the disk and the unit ball, but this is more general.
Excuse me, what is that?
So I'm considering a matrix here, set C, and the condition is given like this. Is the collection of matrices, this is my matrix Z, that satisfy this condition.
Yes, thank you.
Yeah, thank you, to be perfectly clear. So Z is an m times n matrix that satisfies this condition. That's the definition of this domain. It's a kind of like a matrix ball, if you wish. Okay, so in the rest of the talk, more or less, I'm going to kind of restrict to bounded symmetric domains. There are many bounded symmetric domains. I will mention some other domains somehow. Now, relate also Bergman kernel to Lie theory. The automorphisms of bounded symmetric domains, I'm going to explain something about this. There is a nice representations for this, unitary representations for these automorphisms. And finally, more about Toeplitz operators. Somehow in the sense that Nikolai considered, there are weighted Toeplitz operators, but not just for the unit ball, but for arbitrary bounded symmetric domains. So let me explain this. The first thing to notice here is that bounded symmetric domains and their automorphism groups have been classified using Lie theory. Because of Lie theory, thanks to Lie theory, you know precisely which are these bounded symmetric domains. This was done by Elie Carton. So let me explain some of the very basics of the theory of bounded symmetric domains with respect to Lie theory. First, a bounded symmetric domain is called irreducible if it is not the product of other domains. For example, the unit ball, by a theorem of Carton, is very well known to be not a product. However, of course, you can take polydisks, which are products. So that's the notion of irreducibility. Every bounded symmetric domain is a product of irreducible bounded symmetric domains. So you consider irreducible ones. Every other bounded symmetric domain is product of those. So you only want to classify the irreducible ones, like the unit ball. This domain over here is also irreducible. For example, that's another example of an irreducible bounded symmetric domain. Important thing here, for an irreducible bounded symmetric domain, the biholomorphism group is precisely the connected component of the group of isometries. This iso is the group of isometries with the Riemannian metric that comes from the Bergman kernel. So remember that before I mentioned that the automorphisms preserve the metric, so there is an inclusion. But for irreducible bounded symmetric domains, there is identity here. You just take connected component. What is missing? The conjugations, for example, in the unit disk are isometries, but are not by holomorphisms. That's what is just everything that is anti-holomorphic. And you know exactly what kind of groups you obtain here. Exactly the Lie groups, which are simple, as in modern algebra 1, no connected normal subgroups, and non-complex. Precisely these are the automorphisms are precisely like this. Now, if you just consider this condition, non-compact, simple Lie groups, then you get more than the automorphism groups of irreducible bounded symmetric domains. However, if you require this additional condition, the maximal compact subgroups have one-dimensional center, then you have a one-to-one correspondence between irreducible bounded symmetric domains and Lie groups of this type, with all conditions, simple, non-compact, and maximal compact have one-dimensional center. That again was done. And as I said, irreducible bounded symmetric domains are homogeneous by holomorphisms, so you can write them as the quotient of the automorphism group by isotropy of some point. This is always a compact group. For most of the talk, I'm going to kind of assume that D is centered at the origin, circle around the origin. It contains the origin, and I'm going to take K to be the isotropy group of the origin. So have in mind this picture. This is very important. I'm going to use again and again that D is G mod K. An example, just to have this in mind, is this theory of bounded symmetric domains is very, very concrete. It's not just about abstract nonsense theory. For example, for this matrix domain that I mentioned, you take the invertible matrices of this size that are unitary for this diagonal matrix. So this is not positive definite. It has some signature. Take the unitary matrices with determinant 1. That's the automorphism group of these matrix groups. This matrix group, domain, I'm sorry. The action is given by this expression. You can at once recognize that this is a straightforward generalization of the Mobius transformation in the case of the unit disk. So you can write it as a quotient of groups. This is all the automorphism group. The isotropy of the zero matrix is given like this. Just the diagonal matrices. So you take only non-zero in the diagonal, unitary in this diagonal, and the product of determinants is 1. That's a basic example. And for many results, you can keep in mind this particular case. Now, what about unitary representations that I mentioned? The automorphism group of a domain D acts naturally on all holomorphic functions just by precomposing the inverse so that you actually have an action. However, this is not going to be a good representation for the Bergman space. Why? Because automorphisms do not preserve the Lebesgue measure. So this is not going to be a unitary representation. Think of most of the Mobius transformation, they do not preserve the Lebesgue measure on the unit disk. So this representation is no good. So the right way to do it is precompose, but before that, multiply by the complex Jacobian of the function that you use to precompose. Just because when you take the modest square of this, the complex Jacobian, you obtain the real Jacobian variable. So this is a unitary representation of the automorphism group on the Bergman space for any bounded domain. If you consider a bounded symmetric domain, this representation is irreducible. So there are no closed invariant subspaces. Everything. You pick one function, move it around by the automorphisms, closure, linear span closure, you get the whole Bergman space. Because of some features, mostly due to the fact that you're working with non-compact simple Lie groups, you can turn this into a collection of unitary irreducible representations. So let me explain how to do that. You take your irreducible bounded symmetric domain, G mod K, then there is a very specific K invariant function delta from D into the real numbers, so that the Bergman kernel is given by a negative integer power of this function delta. So I'm saying here specific because it has to be defined carefully. I don't want to take much time with this, but there is some special function where P is some invariant associated to D, and it's called the genus. Nothing to do with the topological genus. That and powers of this delta, you can consider some further weighted measures. So here you have your Lebesgue measure on the domain D. You multiply by this function to some power, lambda minus P, and some normalizing constant, so that this is a probability measure. What is the point of this restriction? If you take lambda in this, with this restriction, this measure is going to be finite, so you can actually normalize to a probability measure. Just to explain how things are going on here, I'm using here lambda. Nicolai was using lambda minus P. So there is a shift from the people working with, say, Toeplitz operators and representation theory. Whole family of other finite measures. So you can consider corresponding weighted Bergman spaces. For every lambda with this restriction, L2 with this new measure, intersection with holomorphic functions, this is the weighted Bergman space. For the case of Nicolai and for the unit ball, this delta was just 1 minus mod C squared. And as I mentioned, there is some shift here in the power, because for the weightless case, I equals P. For me, lambda equals P gives you no weight, just Lebesgue measure. For Nicolai, it was lambda equals 0. So there is, as I say, some shifting here. Same kind of properties that the weightless Bergman space had. It is still a reproducing kernel Hilbert space, and there is a corresponding weighted Bergman kernel, which is given by this expression, and you can compare both of this. You can compare these two. With lambda equals P, you have the weightless case. So you have a whole collection of Bergman spaces. For the weightless case, I was able to have an action, a unitary representation. The same is going to happen here. There's going to be a unitary representation on these weighted Bergman spaces. And it is given like this. Because of the symmetry of the Bergman kernel, you compose as before, multiply by the complex Jacobian as before, but with some power, then this is going to be a unitary representation. This is more or less straightforward. The thing is that now you have a way to consider, but it's still related to the Bergman kernel, and you use the symmetry that I mentioned before. Let me go back just a bit. Symmetry over here. Because of that symmetry, you get a unitary representation. With the expression I gave, I'm kind of cheating, because this right-hand side has to lie in the weighted Bergman space. It has to be a holomorphic function. F composed with phi inverse clearly is holomorphic. But what about this complex Jacobian? Before, I had lambda equals P, no weight. So it was the straight complex Jacobian. But now I have a holomorphic function raised to some real valued power. And I want to make sure that this is a holomorphic function. Otherwise, I'm in trouble. So what you do here is really complex variable one. Look for a holomorphic branch of this power. In order to do that, you need simply connected stuff. Otherwise, you're in trouble. D domains are always simply connected, so that's fine. But you have to consider the dependence on the automorphism. And this is going to lie on a connected group, which is not necessarily simply connected. That's a problem. So you go to the universal covering, and doing that, you can actually compute a holomorphic branch of this expression. And you do have a unitary representation. So you have to be very careful. Actually, in the rest of the talk, I'm going to kind of ignore this G tilde and go back to G. But there is some point that has to be considered carefully. Again, these are irreducible.
What is this covering? G tilde.
So maybe with
How it look like?
This example. So the problem with this, the topology of this group is completely equivalent up to homotopy to the topology of this, the maximal compact group. That's one fact. For example, in the case of SU11, the topology is completely contained in the maximal circle. You have to unravel this circle. That's what you have to do. The problem is always with the maximal compact subgroup. For example, SU11 is equivalent to SL2R via the upper half plane. SL2R is homotopic, is actually homomorphic to a cone times a circle. And you have to unravel this circle. All of the time you have to unravel one circle. That's the only problem. This circle has to do with this one-dimensional center that I mentioned here. So that's more or less, it's not very complicated really. You always have to unravel some circle. So the fundamental group in all cases for the reducible situation is always something like pi1 is always the circle, or C2 or Cn, something like that. It would be very complicated. For example, the universal cover of SL2R is not a matrix group, cannot be seen as a group of matrices. So in general, if you want to see here G tilde as some collection of matrices, no, it's not possible. It's kind of, well, not so complicated topologically, but it's a bit complicated from the point of view of linear algebra set. So you have a bunch of irreducible representations, unitary reducible representations. And from some point of view, these are all the square integrable representations of G tilde. So independently of studying Bergman spaces, these representations are fundamental for non-compact simple Lie groups. And as Nicolai did with the unit ball, you have a bunch of corresponding Toeplitz operators. You have a bounded symmetric domain, a weight lambda, an essentially bounded symbol, and the Toeplitz operator, just as before, multiply, integrate against the kernel, but now it's a weighted kernel with a weighted measure, and there's your Toeplitz operator. You have a bunch of linear maps that Nicolai considered very, very well. You have some way to do here a quantization depending on lambda. These maps are injected. And the main point I want to consider here, the main object, are the C-star algebras generated by families of symbols that are essentially bounded. I'm going to denote it like this: T lambda, so it's acting on A2 lambda. S is the collection of symbols. I have a bunch, for the same set of symbols, I have a bunch of C-star algebras. And now, finally, before all this theory, geometry and representation theory, some applications on why this is useful to study Toeplitz operators. So let's take a bounded symmetric domain. There is a non-preserving natural action of G on essentially bounded symbols, just precomposing. You don't need any Jacobian or anything like that here because it's just the supremum norm. So this is the general setup for what Nikolai considered the H invariant symbols. You take any H closed subgroup connected for simplicity of G, the biholomorphisms of D, and consider the symbols that are invariant under the action of H, constant on the orbits of H. I'm going to denote it like this L infinity D H. A nice relationship between these unitary representations I mentioned and invariant symbols. For any bounded symmetric domain, the group of automorphisms is acting on the domain, is acting on the Bergman space, so by conjugation is acting on the bounded operators on this Bergman space, and the map that gives to any symbol a Toeplitz operator is equivariant. The action on the operator is the action on the symbol. So when you have a symbol that is invariant by some G, there is some commutativity between the Toeplitz operator and the representation that you are considering. There is some intertwining property. So the following holds. If you take a closed subgroup, consider the C-star algebra generated by H invariant symbols, Toeplitz operators with H invariant symbols, then consider as before, but restricted to H, all these elements are intertwining operators for these representations. Intertwining means that it commutes with the representation. The collection of intertwining operators is denoted like this, endomorphisms of the representation. So you have this inclusion. The C-star algebra is contained here. In the language of operator theory, if you wish, operator algebras, this is a von Neumann algebra, the commutant of the action of this group H. So this C-star algebra is contained in this von Neumann algebra. Why this is important? H invariant symbols. The first result I know of was given by Korenblum and Shu. They proved that if you consider a Toeplitz operator acting on the Bergman space on the unit disk with T invariant symbol, radial symbols, they can be diagonalized with respect to the monomial basis. But this action of T is just one of three pictures. This picture here, well, I moved the point origin, but the action of T gives you this picture, the dark lines as orbits, the light lines are just the normals, which are geodesic. There are all two other pictures if you consider all possible up to conjugacy one parameter subgroups of biholomorphisms. This is the parabolic case, this is the hyperbolic case, this is the elliptic case that generalizes, as Nikolai mentioned, to the unit ball. And geometry and some Lie theory to prove that Korenblum and Shu generalizes with an if and only if. So the result is the following. Consider smooth symbols that are bounded a self-adjoint subspace, so it's closed under conjugation, satisfying some differential non-triviality condition. There has to be enough non-trivial behavior of the partial derivatives up to order 3. It's kind of technical, but not very difficult, so I won't write it. Then, the C-star algebra is commutative, generated with these symbols. And the symbols are given by H invariant symbols, where H is a one parameter subgroup. So the claim is that these three pictures give you commutative C-star algebras, and this is the only way to obtain commutative C-star algebras generated by Toeplitz operators. There was a question, someone raised a hand. The question?
Doctor, ¿puede poner la diapositiva anterior, por favor? Esa. Sí, hermano.
Question?
Listo, muchas gracias. Thank you.
Okay. So there is an if and only if here. You get from these pictures commutative C-star algebras, but that's the only way to get commutative C-star algebras generated by Toeplitz operators. One way to prove that these are commutative when you have S contained here, H invariant symbols, was mentioned by Nikolai in a more general setup, and this uses one-dimensional Fourier analysis. The way backwards uses geometry. Suppose that you have commutativity for every weight. Remember that I have some shift here with PD genus. Then Berezin quantization, and Nikolai mentioned that, implies that the Poisson brackets, their symplectic geometry, are 0 for all the elements here in S. But we further prove, Sergei, Nikolai, and myself, that this vanishing is also a consequence of the commutativity for every weight. The vanishing of this. Now there is some symplectic and Riemannian information here. The Laplacian is the Riemannian hyperbolic Laplacian, also the Poisson brackets. And the thing is that these identities encode some geometric information.
You should mention that this delta is just Laplacian, not delta introduced before in context of bounded symmetric domains.
Yes, yes, I guess I would have to define the Laplacian for bounded symmetric domains if you wish for Riemannian manifolds. In this case, it's very simple.
Yeah, the point is that you use delta, it's a symbol already in different sense.
Ah, sorry. Yeah. Yes. Yes, that's a good point. It's not the function that was used to define the weighted Bergman spaces. Yeah, this is the Laplacian. Sorry. This is the Riemannian Laplacian for the hyperbolic geometry on D. Okay, thank you. Now, conditions can be used to get some geometric information from the symbols. And here is the geometric information that you can get. This one is very simple, very, very fundamental for any Poisson brackets. The vanishing of Poisson brackets means that the symbols have the same level lines. In this case, we are in 2 real dimensions. This is more complicated. It means that the gradient lines, the lines that integrate the gradient vector fields, are geodesics in the hyperbolic geometry. And this can be seen to be equivalent to the fact that the now back to the level lines have constant curvature. Geodesics have vanishing curvature, but these ones here, the level lines, have constant curvature. So you have a very rigid picture with geodesics and things of constant curvature. This is enough to reproduce these pictures. So all of the Berezin quantization taken up to 1 to degree 3, you get geometric information, and you get that the symbols have to be constant on one of these pictures, and you get the result backwards, the if and only if. So that's one way to use geometry. Another way is, maybe I can kind of go a bit faster here since I don't have much time, and Nikolai already mentioned this. There are constructions like this with these so-called maximal abelian subgroups. This is the result that Nikolai mentioned, actually with more information, with this Bergman type transform. Maybe just mention that there is some further geometric information. The H orbits define a foliation by Lagrangian submanifolds, again symplectic geometry, with parallel second fundamental form. That corresponds to constant curvature. And the normal is totally geodesic. and we obtain some sort of converse, not a full converse, but some sort of converse. If you have smooth symbols that carry the same geometric information, then that give commutative sister algebra, then they come from H orbits. So there is an if and only if you somehow introduce some geometric information. I'm going to show this quickly. Those are the maximal abelian subgroups that Nikolai mentioned with the Siegel domain realization. The thing is that this can be taken not just to the unit disk and the unit ball, but to bound the symmetric domains. That's the next step. If D is an irreducible bounded symmetric domain, consider a closed subgroup connected so that this pair is what is called a symmetric pair. I'm going to define this. Then for every lambda, the sister algebra generated by Toeplitz operators with symbols which are H invariant is commutative. This holds in particular for the biholomorphisms that fix the origin. Of symmetric. There has to be an automorphism of Lie groups so that H is the fixed point set of tau. That's the condition. The proof, well, the idea of the proof, remember that I mentioned that there is an inclusion like this. The sister algebra that we want to show that is commutative is contained in this von Neumann algebra associated to H, and representation theory tells you exactly that this is commutative for symmetric subgroups. So it's, in this case, a straightforward application of representation theory. Examples, there you have them. In the notation of Lie algebras, here is the group of biholomorphisms of the domain. They have some corresponding maximal compact subgroup that you have to mod out to obtain the domain. This is our Carton matrix domain. There are many others. All of the groups corresponding to these subalgebras give you symmetric pairs. So when you take invariance with respect to one of these groups, you get invariant symbols which give Toeplitz operators generating a commutative sister algebra. So that's very important. Explicit Bergman type transform here, but there is one abstract, not specifically written Bergman type transform in the proof of these results. There's something about another way to get sister algebras that are commutative and generated by Toeplitz operators using symplectic geometry, moment maps, and how they relate to symbols. So the thing is that, well, you have your bounded symmetric domain, a group, and out of that you want to get symbols. We saw that with H invariance. If you take H as subgroup of G, you get H invariance, but there is another way. Take H as subgroup. Take an element in the Lie algebra, which is just the tangent space to the identity. There is something called the exponential from the Lie algebra into the group. For our case, it's just the exponential of matrices. So you take this X, exponentiate, get a flow, apply to a point, take the derivative. Somehow, with this construction, your tangent vector in H in the group is taken to a vector field in D. About symplectic geometry. This, because of G preserve the symplectic structure, these vector fields preserve the symplectic structure. And hence, if you insert the vector field X sharp in one entry, you get a closed to form. This is something very specific of symplectic geometry. And it needs the fact that omega is closed and that H preserves omega. But if it is, because this is simply connected. And there's your symbol. Just from the action, you get new symbols, this mu x. Now you put them all together in what is called the moment map for the H action. So here's the definition. So instead of a single symbol for each vector, I'm going to take a whole function that is going to capture all of those symbols. It's going to be a function from the domain into the dual of H that satisfies the following properties. The first one is the way to capture all these mu x. Mu of C lies in space, so you can evaluate on a vector on H. When you evaluate, you get this symbol mu x. And another maybe technical condition which is required for this to work reasonably is invariance. This is the dual of the adjoint representation. It's not always trivial, but for abelian groups, this is trivial and you get invariance. Armando and myself proved the following. For maximal abelian subgroups, the moment can be computed, you have to prove the existence in every case, and it satisfies the following property. Symbol is H invariant. The symbol is over here. If and only if you can complete this diagram. It's invariant if it's a function of the moment map of H. So somehow H invariance and moment map capture the same property. They are the same, but this is for maximal abelian subgroups. If you consider other subgroups, that's no longer true. So I'm going to consider any abelian subgroup and call a moment map function for H any function which is given by the diagram. The set of essentially moment map functions is written like this. Because H is abelian, well, in the case of maximal abelian subgroups, as I mentioned, an arbitrary abelian group, we only have an inclusion. You have less symbols. It's smaller. For maximal abelian subgroups, if and only if H is maximal. I'm here considering the case of the unit ball. This was kind of mentioned by Nikolai. You had T2 for the 2 ball that gives you, with H invariant symbols, a commutative system algebra. But when you move to a lower subgroup, for example, the groups T that Nikolai considered, you no longer get a commutative algebra. There is an if and only if here. So that's a problem with H invariant symbols if you want to get nice, easier to deal C-star algebras. However, if you use moment map functions that depend on the moment map, this is always commutative, no matter how small H is. This is always commutative. So you get a whole bunch of commutative algebras. There is a special situation here with the that is going to be useful to understand why moment maps are relevant. For the unit ball, you have this expression, UN are the biholomorphisms that fix the origin. There are many closed connected subgroups so that this is commutative. The C-star algebra generated by Toeplitz operators with H invariant symbols. For example, quasi-radial stuff given by embedded in UN. However, this is kind of a special of the situation for bounded symmetric domains for the unit ball. If you take any other irreducible bounded symmetric, at least 2 that takes out the unit ball, there are very few or no closed subgroups H in K, the biholomorphisms that fix the origin, so that this is commutative. It's very difficult to have that. Part take smaller groups, the invariant condition is weaker and you get larger C-star algebras. The smaller you consider the subgroups. This is kind of a special of the unit ball. It's not so easy to get the same behavior for other bounded symmetric domains. So the smaller the group, the farther away the C-star algebras are from being commutative. However, this is not the case with moment maps. With moment maps, you can make a small subgroup and still get commutative C-star algebras. I mentioned some results here. For example, this is for the unit ball. There is some work in progress that I'm going to just comment as a general principle with some work in progress that I have with some students. We have seen the following behavior. If you take an irreducible bounded symmetric domain, there are many subgroups H and G, so that if you consider H invariant symbols, the C-star algebra is not commutative. But if you take moment map functions, this is commutative. So there is something special going on here when using these moment map functions. So I'm a bit over my time, but this is all I had to say.
Thank you, Raul, very much for very, very interesting talk. Exactly the purpose, one of the purpose of our this mini conference was to see how rich is the theory of Toeplitz operator, how the theory intertwines with many other very important fields of mathematics. And you wrote perfectly present us the influence and interconnection with geometry, Lie group, and
Thank you.
this is a very, very interesting and important thing. Please questions, Raul. Comments?
Corrections, if you notice another repeated symbol.
Yeah, Harold, for your luck, you don't use normalized Bergman kernel. So your Bergman kernel already used for small k in the first slide. It doesn't matter. Please, comments, questions, come here. If no, Raul, thank you very much again for a very nice talk. And we will see tomorrow. It will be another line of investigation of Toeplitz operator connected with Grudsky. And second talk will be presented for a very nice mathematician, Evgen Sargorodsky from King's College, London. So till tomorrow, be safe, and we will meet tomorrow at the same time.
Yeah. Thank you very much. Very nice talk.